Skaik, PhD student from Parma University in Italy. I'm going to talking about my paper titled the Mass Conditional Text-to-Image Generative Models. Firstly, I will introduce some information about our research field to know what is mass conditional text-to-image generative models, what is generative models, and etc. Then I will discuss or present some information about related works. Then I will present our model and the methodology that we did, and our model architecture, some experiments and discussions. And then finally, I will present some application study and limitation and conclusion. Firstly, generative models is one of the hot topics in our world nowadays, and it's one of the artificial intelligence field that its concept to how to generate new idea from given datasets. You can generate, for example, video from text. You can generate text from another different text. You can generate images from text, and etc. Diffusion model, one of the approaches in of generative models that generate the images from the noise, from noise source data. It has two types, unconditional and conditional diffusion model. When we are talking about unconditional diffusion model, we are talking about generating representative data using only the random noise without any additional data. But when we are talking about the conditional based generative model, here we are talking about generative model that use the noise data with additional information like text, images, and etc. So you add condition to with the noise data to generate new images. Text-to-image generation models or generative models, one kind of conditional model. So if we can see here, we use noise, random noise data with condition of text. That prompt, text prompt, boy is riding on a rocket. We need to generate image for this description or for this prompt, text prompt. So we use here the condition, text condition, a boy is riding on the rocket, and use a encoder to encoding this information with the random noise to training the model to generate these images. This is a general idea about the field of our research. Next, I will present some related works of our research. Actually, there is many researchers and papers talking about this issue, but I will introduce some of them that are very related to our research here. Textual inversion, one of the model that used a view example of image. These images have the same concept, and we need to try to generate a new images for this concept in a new environment, in a new position like this. So the main idea, how to convert this concept inside these images to a new word and use this word with the text prompt to generate the new scene. For example, here we have three photos, three images for toy cats, for toy cat. This cat, we can generate word like S star to present this cat during generation process. So here we have, for example, painting of two S star fishing on the boat. So this is S star present the toy cat in the source images. Another paper, Dream Booth, has the same idea with different methodology and architecture in the model, but had the same idea that we have a view images and we need to generate new scenes for this concept inside this input image. The more challenges paper here that break a scene that has only one image for the training. We know that deep learning and networks need a big or huge data set to train, to learn something. But here we use only, they use only one image with multiple concepts. And they try to generate scenes for one or more of these concepts in a new images. For example, here we used one concept. Here we use they used multiple concepts. For a break a scene, they use a mask. This mask presents the concept inside the original or the source input to specify the area of the each concept inside this mask, inside this image, and they try to generate new images. I will not go deeply in these details because I need to present our contribution here. About our contribution, we generate a model titled Mask Conditional Text-to-Imagegenerative Model, MCGM. The idea of our research that we use also one single image, to generate new images for the concept inside this image. But here we use a conditional, additional condition to diffusion model to specify the position, the pose of the concept inside this images. For example, here we have a dog. This dog, a photo of the S0 represent the dog. The photo of S0 running in the park. How it running? It's running like the shape of the condition that we added. And etc. for all each images in this summarized image. Just to note that we have three type of output here in the picture. If we are looking for the picture, on the top, we have in the final output one concept for each concept inside the source image, S0, S1, S2, S3, each of them doing something different. And here we use mask for two objects, the cat and the dog. Here we use the mask for to generate three objects standing. And here also we generate the output using the two masks. We will present, actually, we will present more results in the experiment part in this presentation. But firstly, I will mention about the model architecture. The model architecture here, we maintain the core of structure of break-a-scene paper model, and we modify or adapt the pipeline of this model to add new condition, the mask encoder condition, to specify the position or the pose of the subject that we need to generate the output for it. In this model, we use two phases for optimization. The first optimization phase for text embedding, we here using text embedding, like here, a photo of asset 0. So in the first phase, we need to optimize the text to improve or to identify the concept with this, to associate the concept with the handler. The handler, I mean the asset 0. Asset 0 here is the handler that handle the concept inside this image. So the first phase, we need to optimize the text embedding to have this issue, to have the mask concepts. In this phase, the model, the Diffusion model is phrased. We need only to optimize the text embedding. But in the second phase, in the second phase, we unfreeze the model to optimize the weight of the model itself. So in the second phase, we unfreeze this diffusion model to optimize the weight inside it. We added the mask encoder for the training process and inference process. For training process, we need this mask encoder to learn the model about the position of the concept. For example, here we have dog, and the position of this dog, we can learn the model by using the mask encoder. And we can use, in addition of mask encoder, the text encoder itself to has embedding with mask encoder to have the final concept that we have. If we have image with multiple concept, so we should have multiple condition or multiple, mask for each concept inside the source image. So the tokens output from the text encoder mixed or added to the mask encoder tokens to present the final concept photo for the dog or for the concept in the source image. Then in the inference process, we need the mask encoder to present the target mask or the target pose that we want to generate. Here we need the mask encoder fed by the mask position for the dog, for example, to generate a new dog with this position. This is the main architecture model that we have. For optimization losses, I will go fast in this part, but just to show that we have 4 losses in the optimization phase. that we have a standard diffusion loss in this formula. Also, we have masked diffusion loss. Also, we have the cross-attention loss. The cross-attention loss, we needed to make sure that each handle only looked to a portion of the image where the related concept is located. For example, here we have asset 0. So to be ensured that asset 0 only look for the part that have the dog, we need the cross-attention loss for this issue. On the final, I will also, in next slides, I will go deeply in this optimization loss, because we during the work we have problem for ambiguity, separating the subject when we use multiple subject in the source image. So we use another or additional cross-attention loss during the training to distinguish between each subject inside the source image. This is the final formula for the losses, optimization loss. And now I will present the most important part in my presentation, the experiments that we have in this paper or this research. We classified the outputs and experiments by two classes. One of them using the source image with one object or one subject inside this source image, and the second class using the mask, or sorry, using the source image with multiple subjects. And for each class, we have branches, we have partitions, and we will present for each case or for each scenario, we will present some outputs. Firstly, during the class, one that have one subject in the source image that we show here. The source input have dog, cat, horse, etc. So there is one subject. We need to use the text prompt, photo of asset 0, for example, sitting on the ground, flying on the sky, running, any action inside to describe the output, what we want, and conditioned or guided by this mask. This is the target mask that we want. For example, here, photo of asset 0 for the dog sitting on the ground. How the dog will sit? Will sit as this position that we guided by the mask condition. So this dog sitting on the ground like this shape of the mask. Also for each example in the slide. A second scenario, we try to generate the same text prompt with different position, with different mask condition to see how the mask affected to this prompt. So we can recognize here that the position of the dog for sitting on the ground it changed during or based on the mask condition that we have. Here, there is a lot of examples about comparing between our work, our results with Brick-Scene or Brick-Scene model, and also with our model with blank mask. I mean blank mask here when I use mask without shape, with a blank area, black area, without any shape inside. So we can recognize here that with using a shape mask, the generated images guided by the mask shape. For example, here the dog sitting in the park, but the position of the sitting not randomly. It's based on or guided by the mask itself, the mask condition. But when using the blank mask, it can generate any position for playing football in different position, in random position. And also for break a scene, the same situation. But in our model with shaped mask, it's guided by this shaped mask in the output. The fourth scenario that we have in one subject example, that we use a photo of a dog. Here we use a dog, not a concept from the source input. Here the dog is a general dog, any dog, but we need to show how it's the mask is affected here. So here a photo of a dog playing football, one statement, one prompt, text prompt, but with different position of the mask. So here playing football, okay, this is any dog playing football, but the position of a playing is related to the shape of the mask. Here playing football with different position related to the mask injected, and also for each example. A second class, when we use the source input with multiple, 2 or more concepts. Here we have source input with two concepts, cat and dog, and we need to generate for each concept a new images, a new scene. And here also we have source image with 2 dog and cat, but with different dog and cat. So we can generate each of these subject in different environment or different scene using this condition. Here we have also different scenarios with different conditions, number and mask number. Here, for example, we have this source input, have 4 concepts. Each mask, as I mentioned before, each mask present one concept that we want. So here we can, for example, generate one of these assets or concepts without using mask. So it can generate without mask. We can use one mask for one object to generate a new scene. And we have here, for example, 2 objects with one mask, the cat and the dog sleeping or sitting in the street in the same position, because I use here one mask. Here also I use the 3 objects with one mask standing for each concept. Here more challenges to have more than one mask in the actions on the condition. So here I use 2 images of the mask to guide the action inside the text for 2 objects. Here we use 2 masks for 3 objects. So we have one mask for 2 objects, cat and the dog, and second mask for the bird flying. We can see from the previous example that we can use different kind of shape mask for different kind of objects. For example, we have mask for a human, you can use it for the dog. You can have, for example, shape of dog, we can use it for cat, for horse, for anything. So it's not mandatory in our model to have the same shape kind or the same shape mask for the same object to have the final result. You can use any kind of mask for any kind of result or subjects. This is one of the flexibility of our model that we have. About population study, regarding the population, we, as I mentioned before, that we, during the work in this model, we have some results that have a problem in distinguishing the concepts, especially when we use the source image that have multiple concepts. So for generating images that have multiple concepts, sometimes the model have a problem or difficulty to distinguish between these concepts in the output. So we can recognize here in the middle with this result that the cat and the dog mix it together in the output. And this is this happened with the model without using the cross attention during the training, or the additional cross attention that we injected during the training phase. And also sometimes it's happened with a brick scene model that we used in our pre-trained model. So by adding the cross attention loss during the training phase, we solve this problem. Finally, I would like to talk about some limitations and the conclusion. About the limitations, here we can recognize in some of the outputs that I presented that some of the results not follow the direction of the mask condition. For example, here we have a prompt photo of asset 0 running for the dog. Okay, the position are the same, that this is our target in the model. Okay, the position is the same, but the orientation is different. Here the mask in the side view, but the output in the front view. So we can see that the position for each output are the same. Position of the creature of the dog here are the same, but the problem here, or the limitation here, for the direction itself. So this is one of the limitation point. And the second limitation point about failing the model to create or a correct position for the concept in the output when we used 3 or more mask conditions. For example, here, photo of a sleeping asset 1 and the flying asset 3 in the street, and asset 0 running. For example, here we have 3 actions: sleeping, flying, and running, and we have 3 positions, mask, to guide each of action. But in the output, we have difficulty to have these 3 action in the output. So in the output, we can recognize that some of these actions not occurred in the output. So this is the one of the limitation that we have, and I hope we will do something in the future. To conclude this presentation, now we have MCGM model that has a powerful tool to generate a high quality image with the diverse mask attribute. This model have a new feature compared to existing or related works that use a single image only for training, and adding a mask injection part to break a scene model. So in our research, we use the mask encoder as a condition, additional condition, to guide the text prompt to generate a specific pose for each subject from the source image. And also the final contribution to solve the problem of mixing a concept together, we added the mask cross attention to training phase to solve the distinguishing the concept problem that we have. Thanks for your attention, and